Hello, guys. Everybody's hearing me? I think so. I'm hearing me, so I will just assume you are as well. So let's get started to talk about monads and function programming in general. So a little bit of myself first. I'm a software engineer at 99 as Valmir, who introduced Kotlin here today. I am mainly a back-end engineer. I build microservices, and also I work with the data engineering team to work big data pipelines. So my main programming language is Scala. I've been doing that for the past 3 years. I also have working experience with other functional programming languages like Clojure. But mostly, my background my programming background comes from dynamic languages like Python and JavaScript and Ruby. So my first experience with monads were actually with Scala, and come from a dynamic language didn't help me, since I did not understand function programming properly. And monads were a distant concept for me as well. In high school, I made a lot of mistakes when I started using monads and working with monads. And I think this talk is all about what I would like to know about monads and how to start to work with them on the right foot. So, why to talk about monads? Monads are becoming a standard in modern languages, and even some old ones. Languages like Scala and Clojure already have implemented into this core some monadic structures, but also some new kits like Kotlin and Swift. So I think it's very important to get into it, to take advantage of these properties, of these structures. Monads allow us to write complex computation easily and without too much overhead. So, however, they are hard to understand because it's a concept introduced by mathematicians. So there is a gap here between the theory and how we use them in practice. So I would like to close this gap a little bit and show you guys how we use them in our daily tasks. So my first goal here is to provide you a soft theory about monads and using analogies. So don't worry, I won't use the burrito analogy anymore. I will introduce a new analogy. I hope it became a little bit clear. Show how we interact with monads through its structures and most common operations, why they are there and how we use them, and provide hand examples of how we can use them in our daily tasks. So by the end, I will do a brief recap of the structures, and we see if everybody got that. So, what is a monad? So I like to think it's like a pill. So it's a shell that protects what's really important, the content of the pill. These shells also provides functionality for the content, like holding it together, providing the right dosage for this content, allow us to safely handle and transport this content. And that is what monads are all about. Monads is just a shell that provides functionality for what is really important, that is our data. Applying that concept to computer science, monads express decisions about how, in which conditions our software should execute. It allows us to handle and route different inputs and outputs without repeating ourselves. And by the end of the day, avoid a lot of boilerplate code. I think we all want that in our codes. Summarizing all that, you can think about monads like a framework to describe and manipulate flows of data. And we know that in our daily activities, in our profession, abstractions matter. Because powerful abstractions makes our code easier to maintain, to evolve, and to read. So monads are more like abstractions how to build these flows of data. So let's talk about some cool monadic properties that we have in monads. First of all, monads are composable, so they have a bunch of definitions on how to combine themselves. You can choose to sum two monads together if you take in the pill analogy back, we can mix together the blue and the red pill to generate a new pill, a purple one, or join them in a list in a correct order. Put the two pills in correct order to consume them in correct order. So in any time, there are some polymorphic. So in any time, you can manipulate the data inside of it, the monad, transforming type A from type B and vice versa. So if we know how to change the red pill to the blue pill, we can do so through the lifting function that we're going to explore here. Another feature is that monads are immutable. So immutability plays a big part in building high-efficient systems. You may know that garbage collection is not a trivial problem in computer science. There's no silver bullet to garbage collection. So languages like Erlang can have more efficient GC because of immutability, since they don't have to search for unused variables from time to time. You just have to clear all variables from the last execution. So that's much more easy GC strategy than other ones. And last but not least, I came too far. Last but not least, monads are also lazy. And what that means, that no computation is actually done until it is needed. So we're going to see how this plays a big part to write powerful software that can be resilient to errors and failures. So most of you guys are probably already using some of the functions that we most use to interact with monads. In fact, many data structures nowadays implement the main monadic laws that you're going to see here, like dictionaries, arrays, sets, and so on. So in this data structure, we are already used to use maps, filter groups to iterate over each element of the list. We also do the same thing with monads. And this function allows us to work on what is really important, that is the content. I will try to extract the content that too much because monads is all about the content that you are trying to manipulate. In fact, all monads are defined by three little functions. The identity functions that returns its value, so here's the get method. The functor that changes its content lazily. And the bind function that allows us to combine monads together. So monads can be implemented as abstract classes. You can think how monads has abstract classes. So you can mix them together using inheritance. Thus, most monadic properties can be applied to several monads itself. So each one of the properties, and that I will explain here, can be used in many monads, many type of monads. So let's enough talking. Let's enough theories. Let's see how the monads are made of and how we use them to solve daily tasks and daily problems that we might have. So first of all, imagine you have a string. You want to calculate its length. You just call a method that calculates, defines a variable, call the length method, and everything is just fine. Then, for some reason, your string is null. You end up with a nice null pointer exceptions. So I think we have all been there. Maybe because we added a column in the database and forgot to handle properly in the code, or improperly handled the inputs of some data that we received. So that's a very common case. So a better way to handle that is through the optional monad. So we can wrap any value that can be null, calculate the length inside the math method, the functor method. So the option type will guarantee that the length will be only calculated when it's possible to do so. We can also provide a default value in case it's become null and we need some value to apply some calculation. Here you can see how monads are lazy by nature. This means that the computation will only be executed when it's safe to do so, without having to write any conditional statement in a purely functional way. So no ifs, no else's here. It's more clear to read this code and understand what's going on. At least I think so. So languages like Kotlin, like Valmir, one of the last presenters show you, also have the optional pattern implemented into its core. Sorry. So we have just put a question mark after the type to mark then as optional, and calculate the length using the question mark dot to lazily apply the method to the variable. To provide the value, just place it after a question mark and column, thus creating a monadic chain like we just saw before in the option in the Scala example. So in Swift, it's basically the same thing with optionals. Just put the question mark after your type, you will be safe. But the lazy operator is already implicit in any method call that you may call into a variable. So you will be safe by default. This not work only with strings, but with any type that you might have in your system. It's a pattern that you can use anywhere. So the continuation monad is what makes possible to chain functions together. And it will be executed in order only if the last one succeeded. A cool example of this feature is a closure sum function, even though it's not a true monad. It's a very cool example. So the sum function will execute a function and pass the result of it to the next one, only if it is not null, and so on and so forth until it reaches its end. This property is called short circuit. In other words, the continuation monad decides if the code is going to be executed or not. Also in Haskell, and other monad libraries that you might encounter, the optional monads also know how has maybe. The cool fact is that you can extend its behavior and handle other values different than null. In this example, we also halt the execution when the string is empty as well. So not only nulls, we are stopping execution also when you have an empty string. Therefore, you can have fine control of the flow that you will execute. So you can extend the monadic behavior based on your content. So whenever you assign a behavior of the monad related to its content, you're using the identity monad, this get method that I showed you in the 3 laws before. So it allows us to create branches of execution based on the content of the monad. It's a way to dictate which path the execution should follow under certain conditions. Here we have an example of an optional query parameter. If it is null, I will fetch all records from the database. Otherwise, I will try to filter these records based on the content of the monad, based on its identity. So you can even use these pattern matches with regular expressions, system types, so on and so forth. In Scala, this is a very powerful way to declare executions flows. Haskell as well. Haskell has the same structures and the same properties as Scala because it has types. If you're working in a language like Clojure, you don't have these utilities in right hand, but you also can implement that fairly easy. Another more general form of this pattern is to catch exceptions in a monadic way. So we can even use the try monad to wrap executions that might throw exceptions, and use its identity to handle different exceptions based on the type it returns. This may, in the first time, may not be too much different from a traditional try-catch statement, but let's explore a little bit deeper to see how we can use this monadic try in more powerful ways than just a try-catch. So the cool aspect is that you can compose the monads in powerful ways. So through functors and the continuation monads, we can build chains of execution that are more powerful. A functor, for those who don't know, is any pure function that somehow uses or modifies the value of the monad. Here we have three functors being applied in sequence to transform the type of the monad. From anything, first we transform anything to a string, then we transform to an integer, and finally to a custom type of my system. And because all these steps can produce a failure, we're gonna wrap each one in a try monad, create an execution chain that will only execute if the last one succeeded, just like the continuation monad. But here the problems arise when we map these functions together. Because the recursive nature of functional programming, you will end up with an instant try of a try. So turtles. Becoming very hard to interact with what's really important for us, that is the content of the monad. But monads are smarter than that. They know how to group themselves properly. So using the flatmap, you can use the bind property, the bind law for the monads to generate a single instance of this monad and gets only the value. So if there's the same base type, so if it's a try, you can bind them together and generate just a one try without the recursiveness. And another advantage of the monadic try is that you can handle exceptions in one single handler from any of the functors. If any functors raise exceptions, you can catch the exceptions in just one place of your code. This is why the monadic tries is far better than a simple try catch, because you can chain together. You can have just one catch exception, and so on and so forth. We can see that how the flat map will behave into this structure. So, moving forward to another monad, the either monad. The either is used to represent values with two possibilities. Is often used to represent a value which is either correct or an error. And by convention, it has two sides, the left and the right side. And we are not talking about politics here. The left side is used to hold an error value, and the right side is used to hold a correct value. Even though you're left-handed, you have to follow these rules. This is used for validation scenarios, where just an exception, does not hold enough information about what happened to your systems. For instance, in parser libraries like JSON libraries, IAM libraries, where this monad is used extensively, the errors types holds information about all the errors that were found in the process of the validation of the serialization. So here's another implementation of the either monad that's called validated. Since you can have special rules about how to join monads together, you can use the screen operator. The screen operator is this weird character combination after the method to greedily apply the functor to each concatenated element in your chain and to combine them in some way that you might like. So the applicative functor is another monadic property. We only join the elements that share the same side. So we can end up with a list of elements that failed or that succeeded in validation stages. This is the applicative functor. Let's see another way to understand that concept. So in contrast to the continuation monad that short-circuit the execution if they failed somehow in the last step, the applicative functor applies the function to the entire data set recursively till it reaches its end, accumulating its results based on either the left or the right side of the result. This means that you end up with a list of invalids or a list of valid values. Also, this property is you may see that how holomorphisms, but don't worry about the weird name. It's just have to understand that instead of short circuit the function, you're gonna accumulate all the results, even though they failed somehow. So with this pattern, we can even use the identity monad with the either to apply different flows after it is executed. In this example here, we return a bad request when the HTTP request is invalid. This means it is on the left side. Or return an OK if it is on the right side. Actually, the either is almost a standard way in libraries like HTTP, Play Framework, to handle user inputs and user validations. It's a very powerful tool to do that. So I think everybody is alive, still alive, yeah? Great. So we reached our last monad, so I don't overwhelm you too much. And the last monad I would like to talk about is the future monad. So the future monad is used to describe a computation that is yet to be executed in a non-blocking asynchronous way. So even that it takes a long time to run, it won't halt your system, so it won't halt the main thread. And this is regardless the concurrency strategy your programming language uses. So it can work with either with threads, coroutines, or even loops. It's more an abstraction of how to write asynchronous operations. Here, this is example, we have the future implementation in Clojure. Again, it's not a true monad because it doesn't implement the three laws of the monadic, but it is immutable and it is lazy though. So I think it's cool. So with the future monad, we can build powerful async operations without having to handle a bunch of callbacks yourselves. So avoiding something that we know as callback hell, a pattern well known from Node.js developers, and express linear computation quite easily. Here in this example, we use the continuation monad to calculate the length of the result. There is a string just after the feature computative is ready. So we didn't assign any callback to do that. So the continuation monad we can be used there to express this linear computation. Also, this is a good time to say that the implementation of the features in Java and Scala aren't true monads. I don't know if you already use features in Java or Scala, but they aren't monads because they aren't lazy by default. So here I'm using a feature implementation called task from a cool library called Scala Z. So another feature of the future monad is that we can choose whether to execute in sequence or in parallel. Using the flatmap, we can use each feature in sequence, as we've seen before, or in an applicative style to run in parallel and handle the return in a single handler. Or why not? Just mix them together. You could do that also. You just have to remember that monads know how to associate themselves, bind themselves properly, so you can build these asynchronous computations quite easily. And because of monadic compositions, you can assign callbacks to manipulate the output of the computation. Even you have a big execution chain, so you can have a bunch of execution that must be executed in some order. So an exception that might have been raised in one of these functions will be bubbled through the execution chain, just like the try monad, but in a synchronous fashion. This is actually a good place to perform any side effects of your system. So like saving a record into the database, updating it, or pushing some value into a queue like Kafka, SQS, RabbitMQ, who knows. So just clarifying that for those who are not used to this term, side effects are operations that change a variable outside of your execution context. So when you update a database, you're changing the word, like we in function programming we said. So we are updating a variable that is outside of our context, but also can be a variable inside your program or outside your programming chain or execution chain. So if you come from a JavaScript background, you might know this, the future monad has promise. I've seen a talk before that explain a lot about promises, and it is the same concept. But promises allow us to exactly control when the computation will be completed. Just in like a case of HTTP request, a feature is completed when it gets a response from the server. Therefore, the promise is finished. The only difference here that the promise API in JavaScript, they kind of aggregate together both the map and the flatmap under the same method. So here, when we try to we apply the done to some execution to create an execution chain for the promising monad, he already knows how to decide to bind them together or apply a functor. So another structure that arose from this pattern and is becoming very popular in the mobile world is the observable pattern. The observable is a synchronous source of data that may never end, or allowing us to build event-based operations through monadic chaining. Since they are lazy and immutable, they are very efficient and are the heart of strings like Akka, Spark, Kafka Connect, and ReactiveX. It may be that they don't share the same implementation, but still they have the same concept of the future monad when you interact with it. They also implement strategies to prevent resource starvation, like here, on the onNext method. We can decide to feed the chain, the monadic chain, only we know it's safe to do so. So we can inspect our memory, our system memory, and see if we still have enough room to process this data. So we can apply some strategy, some back pressure strategy. To handle errors as well on the error method and how we recover from them. And any other events that might happen during the execution. And this is really important. Observables are a great way to create connections with queues like Kafka, RabbitMQ queues, and to handle event sources like pushing a button in mobile applications or applications that handle with a lot of UI. Okay, guys? And observables are a talk by itself. We could spend here the whole conference talking about observables, but we are talking about monads. A bunch of guys consider the observables a monad in disguise. So I think if you think about the observables like a monad, it's more powerful than see just like a structure that you don't know how it works behind the scenes. So other operations that found in strings libraries that you can use are, you can group events by batch sizes or timing intervals. That's very useful to control the execution and how control the exact performance that in the output that your system might have. You can fork the data sources based on types to create substrings or sub-observables that you can share between your code. Or merge two different data sources using some computation rule. And this merging is operation very similar that we have in table joins in database. So we can use a join in a string fashion. Like it's the same thing that Spark does when we're working with Spark streaming, or if you're working with Kafka strings, so on and so forth. It's the same way. So we can also handle errors and applying retry strategies and prevent system flooding, like I said before, providing some back pressure strategy, or even delayed execution. So we can have fine control on what we're going to execute and how and when. So here, a cool example is consuming data from a WebSocket in a monadic way. Here, I use a React-X to create an observable data source. So we apply a connection error strategy, so that we'll try to reconnect just after 5 seconds if we lose the connection. We group together messages that share the same category. And this creates, when we group messages together, we create a flow for each category that might share the same type. And handle only the first message that arrives within the first second. This is the throttle method. There is a way to allow to prevent system flooding. And this flow will only be executed when we subscribe to it. So actually no computation is done until we call the subscribe method. So they are lazy. We can see how complex this operation is, but how simple is to write code and describe it, because all the complexity of is hidden behind the monadic chain. And that's why I say in the beginning of this talk that monads allow us to express ourselves much better than usual code that other than functional programming. So I kind of reached the end of this presentation. I would like to recap the main monads that we explored here today. First of all, I introduced the maybe. They allow us to handle common failure scenarios and their derivatives using the optional and the try monad. The maybe and the optional may be the same monad, but the try is another category. Even I think in Haskell, you can use the maybe monad like a try catch, like a try monad, so may be the same one. The second monad that I show you guys was the either and the validated. They are great for data validation and deserialization. They're used extensively in handling form data, deserialization libraries, and so on and so forth, because they allow us to apply a functor, apply validation to the entire data set in a function program way, in a very efficient way. And lastly, the future monad, which allow us to create non-blocking asynchronous operations. And from the future, we also explore the observables and the promises pattern. So, even that your programming language doesn't have first-class support for function programming, most of the monads are implemented like abstract classes, as I said before. And maybe, if you Google it, maybe there is a library that implements these patterns for you, so you can work in a monadic way. Here we have a bunch of cool monads libraries. We have here SwiftZ and runes for Swift, category for Kotlin, that is an awesome library. We have Scala Z, cats, and Monix for Scala, Lambda for JavaScript, and React-X that is available to almost main programming languages nowadays, even if you program in PHP. One other day I was developing something in Golang, and in Golang you may know that it has a bunch of new statements. So every time you have an error, you have to write if error is new or not new, do that or do something else. And I was, man, why Golang doesn't have the optional pattern? So I Googled it and also find that someone already implemented it. So there are many more use of monads, like the reader and writer, to share state between functions. Let me get back a little bit. So there are much more monads than the ones that I show you here. So we have the reader and writer to share state between functions, between monads. We have monads transformers that allow you to apply functors in each monads. So it's very common to when you ended up when working with monads with a feature of an option. We are trying to fetch some records from the database. So you fetch a record, you return a feature, and the record of the database might or not might exist. So you end up with a feature of options. So and the monad transforms a lot of boilerplate when you're trying to lift the value of this structure. We also have the free monad and the free applicative to build your own custom monads, like we did in Haskell. These patterns, the free monads and free applicatives, are great to build custom DSLs. I've seen guys building not only parsers libraries, but also config parsers. We also have lenses to update nested immutable structures. We have fs, Kleisli, and much more weird names of monads. And when you start to know them, they become very useful. So don't be afraid to dive in and continue to learn about them. So I hope you have enjoyed and stimulated to dive into this fun world of functional programming. So feel free to connect me on Twitter or GitHub, or have a chat with me in the halls. All the slides are on my website or SpeakDerk. So thank you all, guys.